Imagine if our entire planet was sucked into a black hole. What would happen? Black holes, the enigmatic titans of the cosmos, exert a gravitational pull so intense that they warp the fabric of space and time. Nothing, not even light, the fastest entity in the universe, can escape their powerful grasp. Now envision Earth, our blue and vibrant home, approaching this unfathomable force. What unfolds when such an unstoppable force meets our seemingly immovable object? To understand this scenario first, we need to dive deep into what black holes really are. What exactly is a black hole, and how do they form? Let's delve into the depths of one of the universe's most mysterious phenomena. Imagine a star much larger than our sun, reaching the end of its life cycle. This star has burned through its nuclear fuel and can no longer support itself against the gravitational pull of its own mass. What follows is a dramatic gravitational collapse where the core of the star compresses into an incredibly dense point known as a singularity. At this singularity, the density is so high and the gravitational pull so strong that nothing, not even light, can escape from it. This is why we call it a black hole. It's literally invisible in the fabric of space. Surrounding the singularity is the event horizon, a boundary beyond which nothing can return. Crossing this boundary is like crossing the point of no return. Everything is inevitably drawn towards the singularity. Black holes come in different sizes and classes. The most commonly known are stellar black holes, which form from the collapse of massive stars. These are scattered throughout galaxies, including our own Milky Way. Then, there are supermassive black holes, which are millions to billions of times more massive than our sun, and often reside at the center of galaxies. Their formation is still a puzzle, but they play a crucial role in the dynamics of galaxies. Lastly, we have intermediate black holes, whose existence is inferred but less understood. They seem to fill the gap between stellar and supermassive black holes. An intriguing feature of black holes is the accretion disk. This is a disk of gas, dust, and other materials that spirals around the event horizon. As material in the accretion disk spirals closer to the event horizon, it heats up and emits powerful radiation, which can be observed with telescopes. This process reveals the presence of black holes in the cosmos, painting a picture of their immense power and influence. Now that we grasp what black holes are, we can explore their effects on nearby objects. How does a black hole influence its surroundings? Imagine a celestial giant with a gravitational pull so strong that not even light can escape its grasp. This is the essence of a black hole, a region in space where the pull of gravity is so intense that it creates bizarre and extreme conditions. Firstly, let's talk about gravitational pull, and a peculiar effect known as spaghettification. Yes, it's as strange as it sounds. If an object, say a planet like Earth, were to approach a black hole, it would experience an intense gravitational pull. This pull is not uniform, it's stronger at the nearest point to the black hole. This difference can stretch the object, turning it into a long, thin shape like a strand of spaghetti. The technical term for this is tidal stretching, and it's just one of the ways black holes interact with their surroundings. Moreover, black holes have the ability to distort time and space. According to Einstein's theory of relativity, the stronger the gravity, the more time slows down. Near a black hole, this effect is so extreme that time could theoretically stand still. This warping of space-time is not just a theoretical curiosity, it could have real effects on anything that ventures too close. Finally, tidal forces around black holes are immensely powerful. As Earth would get closer to a black hole, these forces would become more pronounced, eventually tearing the planet apart even before it reaches the event horizon. With these powerful effects, let's simulate Earth's journey into this cosmic blender. Now, picture Earth slowly drifting toward a black hole. As our planet approaches this cosmic behemoth, the first noticeable effect would be the intense gravitational pull. The black hole's gravity isn't like anything we've experienced on Earth. It's a force so strong that it begins to pull more fiercely on the part of Earth closest to it. This creates what are known as gravitational tides, which are vastly more extreme than any ocean tide caused by our moon. Imagine the Earth, not as a solid sphere, but as a slightly malleable object. These gravitational tides would start to stretch the planet. Initially, this might not be visible to the naked eye, but the effects would be devastating. Volcanic activities could increase, earthquakes could become more frequent and severe, and our planet's orbit and rotation might start to show anomalies. As Earth draws even closer to the black hole, the stretching would intensify due to a process known as spaghettification. Yes, it's as strange as it sounds. Spaghettification is when objects become elongated under immense gravitational forces. For Earth, this would mean being pulled into a long, thin shape, ultimately tearing the planet apart. This isn't a quick snap, but a gradual and violent pulling apart of everything we know. From the perspective of someone on Earth, the sky would likely darken as the black hole bends light around it. The stars would warp in the night sky, and then, one by one, they would disappear, swallowed by the growing shadow of the black hole. For an observer from afar, they would see Earth stretching and fading, its light struggling against the inevitable pull. The experience would be beyond anything we can fully comprehend from our current understanding of physics. As Earth stretches and distorts, the final plunge would be both spectacular and terrifying. What happens when Earth finally crosses the event horizon? This is where our journey into the black hole takes a turn into the profound unknown. As Earth approaches and eventually crosses this critical boundary, known as the event horizon, the rules of physics as we understand them begin to warp and twist in unimaginable ways. The event horizon acts as a point of no return. Beyond this, not even light can escape the immense gravitational pull of the black hole. Here, the familiar laws of physics start to break down. Traditional concepts of space and time cease to operate in ways that make sense to our everyday experiences, or even our most sophisticated scientific instruments. As we delve deeper, we encounter the idea of the singularity, a point at the center of a black hole where, theoretically, gravitational forces compress matter to an infinite density. The laws of physics as we know them simply don't apply in these extreme conditions. What occurs in this realm is one of the greatest mysteries in physics. Adding to the enigma is the information paradox and the firewall hypothesis. These theoretical concepts challenge our understanding of information retention and destruction within a black hole. The information paradox puzzles scientists by suggesting that all the information about matter swallowed by a black hole is lost forever, contradicting quantum mechanics. Meanwhile, the firewall hypothesis proposes a violent and energetic boundary that incinerates anything that dares to pass through the event horizon, potentially resolving the paradox but introducing new questions about the nature of reality itself. Once Earth crosses into the event horizon, it's a journey into the unknown, with no chance of return. With Earth gone swallowed by a black hole, what's the broader cosmic impact? As we contemplate this hypothetical scenario, it's intriguing to consider how Earth's disappearance would affect the remaining architecture of our solar system. The Earth contributes to the delicate balance of gravitational forces that govern the orbits of the planets. Without it, there would be subtle yet profound shifts. The immediate neighbors, Venus and Mars, might experience slight changes in their orbits due to the sudden absence of Earth's gravitational pull. These changes would ripple outward, potentially altering the trajectories of asteroids and even comets in the farther reaches of the solar system. Moving beyond the immediate physical impacts, let's theorize on the human aspect. If humanity were to survive this catastrophic event by having established colonies elsewhere in the cosmos, how would they observe or even continue after such a monumental loss? From a distant outpost on Mars or a space station in another system, humans might watch through powerful telescopes as the last light of their home planet gets sucked into the abyss of a black hole. This event would not only be a spectacular and solemn spectacle, but a poignant reminder of Earth's fragility in the cosmic dance. This leads us to a more philosophical reflection. The transient nature of celestial bodies, including our own planet, is a humbling thought. Stars are born, they live, and they die. Galaxies collide and reshape. And perhaps planets too can meet their end in the maw of a black hole. In the grand tapestry of the universe, everything is temporary. This realization might seem daunting, but it also connects every one of us to the most fundamental truths of existence. We are all part of a much larger, ever-changing universe. While the thought is overwhelming, it underscores our place in the vast universe. So, what have we learned about our planet's potential fate in the grip of a black hole? We've delved into the dark, dense world of black holes, understanding their immense gravitational pull. We've pictured the dramatic end Earth would face, torn apart and swallowed, leaving nothing behind but cosmic echoes. This journey highlights not just the destructive power of black holes, but also the broader, awe-inspiring dynamics of our universe. It underscores the importance of astronomy in decoding such profound mysteries. Though it's a scenario of cosmic proportions, it's a fascinating glimpse into the powerful forces that govern our universe.